All right, 2018 free response question number 1. This one is a little bit of a variation on the classic input-output problem. We're talking about people here and not something like heating oil, which we've seen in the past, but we're talking about people entering a line for an escalator at a rate modeled by this function. So this r of t right here is going to be your input function here. And very often in a problem like this, they give you a separate output function and they explicitly define that. But in this case, they go ahead and just tell us this little bit right here. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. So that sentence right there is really used then to give us our output function of that 0.7 people per second right there. So that was kind of interesting. And then something you always want to look out for, almost always in an input-output problem, there's an initial condition that they're going to give you, and it usually comes either at the very beginning or in this case at the very end of the setup, the stem for the problem right there. So I always like to circle that, because that's a really important piece of information that, honestly, you can do the whole problem without it, and there's no real clear indication that you've missed that or forgotten it until you look and every one of your answers is wrong, and pretty often that's the case. So we've got 4 questions to answer right here, an A and a B and a C and a D. Let's get started on this first one. How many people enter the line for the escalator during this interval from 0 to 300 seconds? Notice this is a separate question than what they're asking in part B. And C, how many people are in the line is what they want to know at part B. So in A, they don't really care about the initial condition. It doesn't matter how many people were there at the start or at the end. They just want to know how many people entered. So that's a question that is just related to the input function. So for part A, let's take a look. We took our r of t function, which was measured here in people per second, and we just want to know how many people that we're going to have at the end. So to go from a people per second rate function into just plain people, we're going to do a definite integral now. The time interval we're talking about is from 0 to 300, so we're doing a definite integral from 0 to 300 of r of t taken with respect to t. Think about units for a second. R of t is measured in people per second. We're multiplying that by dt from 0 to 300 seconds. So this is people per second times seconds, which is going to give us just plain people. I just typed this into my calculator and that was it. So remember everybody, this is as much work as you need to show and as much work as you should show on a problem like this. Notice I didn't include units either. The question said how many people, but it did not say anything about including units, so I just left my answer as 270, and that's it for A. Okay, for part B now, during that time interval from 0 to 300, there are always people in line for the escalator. I found that to be an odd thing for them to tell us. But now the question, how many people are in line at t equals 300? So with an input-output problem, we've talked about this before, everybody, there are 3 things you have to consider to answer a question like this. The first consideration, how many people were there or how much capacity was there for whatever it is you're measuring at the start of your time interval. You need to add to that the number of things or people in this case that have been added during this interval of time. And the third thing, you need to subtract then the amount that's been taken out of this particular quantity or function during that time interval as well. So with those 3 considerations, let's get working on this one. For B here, I'm trying to do this in chronological order here. 20 is the number of people we started with. We added to that the number of people who entered the line from 0 to 300. Well, that's the exact work that we did up here in part A. So we started with 20 people. An additional 270 people have gotten in line. I should not have written this right here, and I should have kept going now. And then subtracting from that, and this is the first time we've kind of spelled this out, our output rate is 0.7 people per second. So we're just going to multiply 0.7 times the number of seconds that have passed on the interval from 0 to 300. And simply typing 20 plus that 270 minus the 0.7 times 300 in the calculator got us an answer right there of 80 people that were in line at t equals 300. Okay, so that takes us through part B. Let's take a look at what's going on in C now. So for t is greater than 300 now, and the important thing about that is your input function drops off completely now after 300 seconds. There is no additional input here. No more people get into line after that 300-second cutoff right there. So when t is greater than 300, what's the first time t that there are no people in line for the escalator? So this is actually going to work out similar to what we did in B. We want to know when the total number of people in line is equal to 0. So we're going to do kind of the same consideration that we did here a minute ago. In part C, we start off with 20 people that were in line at the beginning of the day. We add the 270 people, again from part A, that entered the line between 0 and 300. And because, let's go back to the input function here, because r of t is 0, we don't have to add anything additional above and beyond that 270 right there. That's it. Those are all the people that are going to get in line right there. And then we need to subtract the total number of people that get out of that line between 0 and t seconds. So instead of a 0.7 times a fixed value like 300, now that's our variable. So a minus 0.7t, and we want to know when that total number of people will equal 0. So just cleaning that equation up a tiny little bit, bring the 0.7t to the other side right here, and we get 0.7t equals 290. Divide by the 0.7 right there, and we find that the number of people in line will equal 0 when t is equal to 414.286 seconds after this whole little experiment begins. Okay, and that takes us through part C, and let's go to D, which was by far the most complex part of this problem right here. Okay, so in part D, they want to know at what time t is the number of people in line a minimum. In almost every input-output function problem that we do, they're asking you to find a minimum or a maximum. This is something they're very interested in knowing that you guys know how to do. So that's one question. At what time? That's important right there. But they also want to know, to the nearest whole number, find the number of people in line at this time. And then, as we talked about a little bit on our chat yesterday, justify your answer. Doesn't mean that we need a big verbal explanation. We just need to show all of our work right here and show them that we thought about everything that needed to be considered. So when we talk about a minimum or a maximum, those can occur at two different places: endpoints and critical points. And we need to demonstrate to our grader here that we've thought of both of those things. So let's take a look at part D here. First thing I wrote down, just to communicate to the people grading this that I know what I'm doing, check endpoints. And that occurred obviously at 0 and at 300. I haven't checked those yet, but I will pretty soon. I also want to find critical points. And critical points are the times when your derivative of your function is either equal to 0 or is undefined. And critical points in a case like this are going to happen when the input rate, r of t, in people per hour is equal to the output rate here of 0.7 people per second. When the input and output rates are exactly the same, think about filling a bathtub with the drain still open at it. If the input and output rates are exactly the same, then in that bathtub example, your water level won't be rising or falling. It'll be staying exactly the same. And for us, we're interested then in knowing when the number of people there is exactly staying the same right here. So to find critical points, we want to know when our input rate is equal to the output rate. Well, the input rate was measured by the function r of t, and the output rate just remains constant at 0.7 people per second. So I put that into my calculator and solved that and came up with these two values here, 33.013 and 166.575. Okay, so beyond that right there, these are now the 1, 2, 3, and 4 values that we need to test the number of people in line for. So I kind of made up the name of a new function right here, p of t. A lot of times I use p for a population function. In this case, it's just people as a function of time. And this now kind of harks back to what we did in part B and part C here as well. So if we want to measure the total number of people in line at a particular moment in time, here's what we did. 20 was the initial number that we started with. We're going to add to that the integral from 0 to t right here of r of x dx. And then we're going to subtract a 0.7t from that result. So this is the number we started with, plus the number that got into line, minus the number that got out of line. So that'll give us right there the number of people in line at any time value t. All right, and from there then, everybody, let's take a look at what we got. We went ahead and measured p of 0, and just to make sure things were right, I did go ahead and define this in my calculator, and then I went ahead and typed in p of 0, but I think we knew from the initial condition already presented right here that that number was supposed to be 20, and sure enough it was. So here we go, that p of 0 was equal to 20, that wasn't a surprise. Went ahead and typed in p of 33.013. Quick note on this, if we really wanted to be accurate about this, we probably should have gone back to this value right here and stored it in our calculator, let's say as A, and then typed in P of A right here. I'll tell you guys that I cheated a little bit. I went ahead and just manually typed in P of 33 point, and I went ahead and typed in a few extra decimal digits here just to be more precise. So instead of 0.013, I'm away from my computer right now, but I think I typed it into like 6 decimal places just to make sure, and found that the number of people in line at 33.013 seconds would be 3.803. So that number went down pretty significantly. Then we measured our second critical point of 166.575 seconds, and again I typed in a few extra decimal places there and got 158.070 people. And then lastly, at the end of this time interval, at p equals 300, well, this goes all the way back to our answer from part B, but again, I double-checked it in the calculator, and yeah, got 80, just like we did a little bit ago in part B. So with these 4 values, these are the only 4 spots where there could potentially be a minimum or a maximum. So I went back and read the question again. They wanted to know at what time of t was the number of people in line a minimum. So the minimum, it looks like, occurs right over here at this second of our 4 potential candidates. So in answering the question right here, the number of people in line was at a minimum at a time value of 33.013 seconds. But they also asked us to the nearest whole number, find the number of people who were in line at that time. So they did also want the y value, or the p value right here, rounded to the nearest whole number. We said there would be 4 people in line at that time. And the directions do say to justify your answer, the amount of work that we've shown here in part D is more than sufficient right here to show them that we considered everything we needed to and to explain why our answer was as such.